bit slow today, a little bit later. How one of my teachers said, if we start later, we finish earlier. That's based, yeah. Oh, probably the microphone is not the one that I properly chose. No, everything's fine. So, at the last time I announced to you that we were going to talk about pipelining and symmetry breaking.
Mm-hmm.
So we will start from it today. From the beginning, we are talking about pipelining. By the way, there are some problems. Someone has had problems with the homeworks because they didn't explain how to write it in fork join model. They decided that they're too smart and then explained how the processor is working without spawning them. So they're kind of the correct algorithm, and the real one is a little bit different. So about pipeline, what would we say? So suppose we are in the car factory. Okay.
Okay.
We are in the car factory. How car looks like? It has a bottom, two wheels, and the top of the car. It is looking like a race car, but we are trying to do it massively.
Mm-hmm.
So what's happening here? What will be our task to show the pipelining? So we will be going with 2-3 trees, which you should have been reminded by looking at Wikipedia. And we want to insert M elements. M elements sorted. So we are given a sorted array of their keys, and we need to insert it.
Mm-hmm.
No. Okay. So let's talk about simplest approach, and then we will go back to the factoring. Like I thought that it will be nicer right now. The algorithm is pretty simple. What we're doing at the start. At the start, for each element, we find the position where it should be in this data structure.
Mm-hmm.
So it should be like some here, some here, some here, some here. Okay. The issue with the insertion of M elements is the following: that all their elements can potentially get to one parent.
Yeah.
That is pretty awful to do, because you have to, like, it doesn't work as the normal 2-3 tree where you just add one element and like going upwards and fix everything.
Mm-hmm.
Okay, so we have to find a way on how to add elements in some order, so there is no such problem. By that I mean that only one node only one element can be between two keys that are already in the tree. So suppose for a moment that we have a very good range of elements, and each element appears exactly like only one element can be between two consecutive keys. Okay, so what's happening here? Here we don't have. The very interesting thing here is that if we have 3 children in the node, and we have 3 elements to be inserted in this small tree, it will still work as the normal 2-3 tree. Because what we're having here? We're having here like 6 nodes at the worst, which we can split onto 2 nodes with 3 and 3. So we still have the same intuition from the 2-3 tree, is that in the 2-3 tree we have, if we have 3 nodes and we insert 1, we split it into 2 with 2 children. But instead right now we could have 6 children, and instead of splitting into 2, we split into the 2 by 3. So nothing really changes in the terms of them. Yeah, I understand it becomes a little bit more complicated, but in terms of the tree, this will create only 1 new node per level. So if we add here, so we have this one to split, this one to split, this one to split again, right? And there are like you have again at most 6 elements at this guy. When you split here like that, and here like that, and here like that, you again have at most 6 of these guys. So you can go up and continue their insertion of their elements. So again, if the nodes are inserted in a way that between each keys there is only 1 insertion point, then we can do simple 2-3 tree going from the bottom, like each level by level, using parallel 4. I think this is quite clean in the terms like.
No. When we insert, when we can't split nodes in parallel because no. Okay. Let's say that our fork join goes to the same node from different subtrees.
Okay.
And how they decided which thread should truly divide our node.
Yeah, that's a good question. So specifically for that, you have this list of nodes, and then you insert there something, and then you say, okay, I have to split this guy, and this guy. Okay, so I have to, there are 3, 1, 2, 3 threads that are wanted to split this element, right? This idea is named reserve commit. To be honest, is that when you write an identifier of the process in the special cell here, like 1, 2, 3 trees, going like that. Okay, I will say that I win this time, and they kind of in parallel 4 they try to write here their identifier. Only 1 will succeed there.
Okay, yeah.
And then this guy will perform their sequential split of the elements. The restructure.
And other threads, what will do?
Nothing.
Okay, yeah.
Yeah, they kind of reserve. This is named reserve. Reserve their ID, the thread that is going to sequentially perform, and then we run the same again the parallel 4, and these guys check who is the boss of this gym, and then this guy kind of wins and perform the sequential change. Yes.
When we talk about one thread winning the race, do we talk about some of CRCV modifications?
No,
or
we
they have
are
consensus
we are working in the real world system right now. So like in general, you can write from their separate threads into the same cell, and like one of them succeeds. Like, right? That's the usual model. Luckily here, it will, like as with maximum, we had their issues that and elements were writing at the same time in the same cell. This is kind of not very good because you have, like, for example, if you have n processors and you want to write all their values to the cell, it will cost linear time. Okay, if there is
because
n
we have
processors who are trying to write this down, this will cost all of n.
because we should get unique log on cache line to do it.
Yeah, because kind of not unique log. This cache line should be in exclusive mode in missing or like any other version. So this will be linear. Luckily here we have only constant number of guys. So in the terms of the complexity, it will not change anything. Okay. So what we are doing here, so we go level by level, and then rebuilding the tree. Okay. Unfortunately, this doesn't work in the terms that we can get all the elements somewhere into one. So like we cannot use our algorithm here. Because we exactly rely on that there will be only 3 new nodes, 3 new children to the node. So do you have any idea on what we can do?
Seems like
By the way, we haven't told about the complexity of this algorithm. We haven't talked about that.
Work seems to be not more than linear.
Work is to be more precisely like that, right?
Log and
and plus n, right? So like that's
yeah, agree. And span.
What is with span?
Seems logarithmic of n plus m, because in common case on each next level we will leave some threads to do nothing.
Okay, the simplest, if you calculate this, the simplest one, it will be like that. Okay? Log n times log m, because you have log n levels, and in each you have parallel 4. That will give us log n times log m.
Okay, yes.
Of course, you still can use here the trick that like you can spawn, like in the scan algorithm or like that, you spawn the proper number of threads which are later kind of getting back. But you need like here you need to calculate, like that. You simply just go downward, like fork join, but you sometimes have fork 3 join, which can be emulated, right? Like we can go downwards and then we go backwards. So typically you can change it to the sum here. No, or you can, or you can't. It's a good question. Because right now I will exactly explain how to do this in their sum. So like that. And for that we need pipelining. but possibly you can do this without pipelining. Could we do that? I think you can. But like it's much complicated, of course. Okay, let's go back. So between two elements we have a lots of insertions. So what can we do?
Split our 3 on the leftest element of which we insert, and the rightest element of
Okay, yes, and yeah, I understood you.
and on our elements that we want to insert, we just build a separate tree. So we have 3 trees that we have to merge in some way. How to do it?
That's reasonable, but I'm trying to ask a little bit different thing.
We can
That in which order I can insert these elements? In which order? So that each guy is between two keys.
probably we can insert middle element, then middle of middles.
Yeah, yeah, exactly. So you should insert the middle element. So you just insert the middle element, then insert the middle element, then you insert this guy with this guy, and so on, right? Kind of recursively. This is fine with us because when we insert the middle element, it becomes a key. So this guy and this guy already has kind of their two keys that he's between, because like this is already like kind of this is their key. So these guys, when you insert these guys, they will be separated by this guy, and that is why you can get it up. So what's happening here? So we have logarithmic m. Okay, we have logarithmic m for each part, which we insert consequently, so it will be log n log m. So if we use that span, right? So like you're inserting them one by one. So in total it will be logarithm squared m logarithm n. Okay, that's not what we really want. We want it a little bit faster. What I suggest to do, okay, like let's look on the car right now. So suppose that in our factory we have several conveyors. There is a conveyor that creates bottoms, like I don't know, like their wheels, and the top of the car. Okay, so you come and you are going from left to the right. We are trying to build a new car there. So what's happening here? At the beginning, nothing really happens. We have the bottom of the car here. Then we move this here, and then we move it here. Okay, but while you move it here, like from the bottom to the wheels, we could already starting to do another machine.
Yeah.
So kind of instead of waiting each time while the whole car is complete. We kind of doing like level by level. So kind of we have a bottom, like at each moment of time we have three machines ongoing, like the one that do bottoms, the one with the wheels, and the one that is full. Okay, how we can use it here? Pretty simple. So we decided to add the first element, then two middle elements, then so on. Luckily for us, the reconstruction of the tree is, how to say that, is local, right? So when you add your element, you only affect these guys, only parent and the grandparent. In the worst case, I think even the grandparent. No. It should be. The grandparent should be there. So you can see that when we insert an element to the lower level, we change this guy and this guy in the worst case. So kind of we have.
But
No, we don't need this. I think we're going to insert later.
no, we affecting all the paths to the root recursively.
Yes, recursively, yes. But if we start putting, like, you can see that at the beginning when you insert all the elements, you only affect the guy that on top of us.
It's moment, okay, yeah.
At each moment, yeah. Then you go to this level and you have to insert that. You again affect these two guys, and so on. So that is why you have an idea of pipelining here. You first insert this middle element. It goes, I don't know, somewhere here and somewhere here. Okay, and we stop for a moment. So like the middle guy made only 2 steps. Then when we add new elements, the operation on this guy isn't affected because he's much higher already. At that moment we continue with the guy here and 2 guys here, like the second ones. Again, do 2 steps, and then okay, we can add the next level on inserting elements. Then we insert, and so we're going the same way. So instead of multiplication here, we will have add sign. I think so. It should be something like that. I mean, you anyway should lose. There's the power of the logarithm. Let's calculate it. So the work is still the correct one. I think this is kind of clear. The idea of the pipeline is that like the things that we're not doing are not intersecting with each other. So that's main, and then we have logarithm m. We have parallel 4. We have parallel 4 at each 2 steps here. We have parallel 4. So it is logarithm m, and how many times you should do it? You should do it logarithm n plus logarithm m times we push the elements to the tree. So you get squared. So you have this span here. Again, we have on each step we have logarithm m span due to the parallel 4 of the elements that we're going to put to their level up by 1. And then on each, like how many times we should do this? We should do this logarithm n times to put like the new element to their top. And at the same time, it is logarithm m because here you insert these elements in logarithm m steps. Thus, in total, you will get this complexity.
Okay, theoretically it's clear, but
Yeah,
I have no ideas how to write it.
I have neither. I have neither. Like this thing with six guys is already kind of complicated thing. With this reserve and commit thing, that's really hard to implement.
So nobody has written it.
Yeah, I think so. Because there are much simpler approaches than this. The problem with the 233 is that it has the same height. That's a little bit complicated in terms like if you want to. I will explain in some lecture, like in 5 lectures, I will explain how to do this on binary search trees with a good complexity. Okay, this is about pipelining. So the question that is going to home is that how we could delete m elements. So we insert in m elements, and now I'm asking you how to remove them. Seems reasonable task.
Just idea without.
Yeah, just the idea. Yeah.
Seems okay.
You have to think a little bit about that. It's possibly it's. I mean, possibly it is trivial. I wouldn't say. I wouldn't say that this is hard.
Okay.
I wouldn't say that this is hard. But pipelining indeed works. So at some point I solved some tasks specifically on that. So where you could put into the conveyor belt, and it works faster, of course, than anything else. Okay, now we will consider symmetry breaking. You could say that this is impractical and doesn't make sense. I would agree with you, but some algorithms unfortunately need their symmetry breaking. Okay. You are given a cycle. We're given a cycle which is stored as array next.
Okay.
We have an array next. Quick question: how I can get pref? Can I get pref array?
Do we know the size of the cycle?
Yeah, we know that it is the size of n. Like, and their identifiers from 1 to n.
No, or just
Next of ID minus 1 mod n.
No, unfortunately, these guys can be in random, in chaotic order.
Then next for n minus 1 times.
no. We just can go through the cycle and for each node save that current node is the previous of the next 1.
Yeah, so you simply go the parallel 4 and say this. Nothing else. Like, that's simple. That's how you get the previous. Like that's sometimes helpful. So what is the key idea of the symmetry breaking? Is that we need to color each vertex. You have to color each vertex with a color such that it has no neighbors with the same color. So we kind of want to do independent sets. Find how to split this cycle into independent sets. Okay, let's remember what is the coloring number, chromatic number of cycle?
2.
Minimal number of colors that.
You have no idea?
I have no idea what is chromatic number.
Chromatic number is the smallest number of colors that you can color the graph so that it has no neighbors of the same color. So this is exactly what we are trying to do in this symmetry breaking.
It depends on size.
It depends on size, but like at the worst case,
3.
it's 3. Okay.
Mm-hmm.
So we will try to color the cycle in 3 colors. Okay. Okay. How we will do this? The algorithm, unfortunately, the algorithm uses that the bit operations on 2 integers are constant. So I need to say this in advance. So like the OR of 2 elements has the same constant complexity. I mean, it is reasonable on the current machines, but in general, this is quite, especially if n is too large, you cannot do this faster than logarithmic n. Okay, we will do now a pretty interesting thing. So we take a guy and its next guy, and we consider like this guy has identifier X, this guy has identifier Y. And what we are doing, we take X as the binary string. And this guy, we suggest it has some other. So what we're doing, we color Y in an interesting color. So color Y will be equal to min bit, where X not equals to Y, plus this bit. So for example, for these guys, we have the first bit the same, the second bit the same, the third bit are different. So we put it here as 3 plus the bit here, the bit is 0. That bit, I mean exactly that bit, it's 0. The most interesting thing about this coloring, let me change this a little bit. For future it will be color of X, color of Y, color of Y. This way we recolor all the elements, and one can see that these new colors will be not equal. Like two consecutive elements on the cycle will have different colors. Why so? So we have X, color X, so this guy is X, color Y, and color Z, okay?
And what are the colors in the beginning? The ID?
Yeah, at the beginning the colors are the identifiers. Okay, at first, if the smallest bit is different, then the new color of Y and new color of Z will be different, because like this will be the main part of this new color. So if these two colors has different bit with this, then we're done. Like new color of Y and new color of Z will be different. Okay. Suppose that they're different in the same bit. But if they're different with the same bit, then color Y and color Z will have different bit here.
Yeah.
That is why the new colors will be kind of not unique, but we can color the cycle so that none two vertices with the same color are neighbors. Okay. So we start with n colors. Then we color everything. We get 2 logarithm star of n. Oh, sorry, logarithm of n. But I think you're understanding what's going on later. Then it will be log 2 log 2 log n and so on. And apparently it is logarithm star n. No, I mean not like that. We finally got to the constant, and the number of these iterations is logarithm star n. The problem with this, there is a tricky thing with this approach is that this C is not so small. So we are targeting for 3 colors, but unfortunately we can get worse. Because for example, if you take 8, you have 8 different colors. Then the new color will be 2 times 3, because like we have 3 bits. For 8, we have 3 bits, so like it's 2 times 3 plus 1, so it is 7. By that, like if currently the number of colors is 8, you cannot get lower. You cannot get less colors. But luckily, we can split these vertices into the groups of the same color. So we have the first color, the second color, the third color, and so on, like 8 like let me say that there are 8 colors. Be more precise, C, so, because we put here C. And then we will start to put these elements back to the cycle. So kind of you take them away, and now you are starting to put it back. So you put the first elements, everything is fine because they are disconnected, so everything is fine. Then 2, we add elements 2, everything is fine. We add elements 3, everything is still fine because we know that we properly coloring that. Now we are coming to the elements of the 4th color. What's happening there? When you put a guy from the 4th color, like it was color 4, you could look for the color of this guy, of the previous, and the next. And if they already have colors, you can choose the 3rd color for this guy, which is different.
Yeah.
And we can do the same in parallel with all the elements of the 4th color, because they're not connected. We know that our previous coloring was perfect in the terms that none of the two vertices has the same color, two connection vertices. Then this means that you can never have like two nodes with 4 color adjacent. Then you have this guy and this guy, and they are you can choose their proper color for this one when you add it, and you like continue adding them kind of color by color. The problem with that approach is that what is its work?
In the beginning, we have
N. We have n elements with identifiers from 1 to n.
yeah. So each of these arrays is filled with one element.
There?
Yes.
No. We perform logarithm star rounds. So
we
that the
we start coloring and then
yeah, we start recoloring using this approach. Using this, so like you start from n, you get 2 logarithm n. The number of colors is 2 logarithmic n. Then you take this logarithmic and so on. At some point, you will have only C colors. And the length of this number of elements is logarithmic star.
Yeah, and on each step we have O of n operations, so n log star n.
Yeah. Alexander, do you understand what's
yeah, there is no question with complexity. I just don't fully understand when we start putting our elements in this color arrays.
Okay.
When we have already colored all of them, or when we
okay, let me explain again. So we are trying to shrink the number of different colors to some constant. Okay,
yes.
And then you have C arrays. Like in each array, we have the nodes of this color, and then we try to put them back to the graph. Okay. So at first we decrease the number of colors to C, and then we want to have only 3 colors. So you just have the arrays, like you filter them, or like in which manner you want. You could because this is a constant number, you can filter them. Like you have an array of colors, and you can filter the identifiers that have the color, the corresponding color. And then we start, like when we get this, we start to recolor everything. So the first, second, and third colors are fine because we need to have 3 colors. And with the color 4, we just put each node back and check its neighbors.
So firstly we determine what are the colors with this procedure, and then knowing the colors, we recolor them into 3 colors.
Yes. But again, this C is constant. It should be constant, otherwise this will not work. Yeah. Okay, so the work is n log star. Okay, what's with the span? If we consider that this thing is of 1. I mean, you typically can do this of 1 per reasonable integers. Like lowest and highest bits. This is
okay, firstly we have log star n rounds, and rounds are performing consequently, so we have to count the span of each round. Hard. No, okay. Any ideas?
Probably each round is O of 1, because we can count this in O of 1.
no, each round unfortunately not they're of 1 because you have to make parallel 4.
Parallel 4, so log n.
Yeah. So the complexity here
Log
is
star
log
n, log n.
star n. Yeah.
Uh-huh.
But the problem is in here, right? Because you can color the cycle much faster, like in linear. Like if you want, you can do this in linear time. Obviously, this is not what exactly we want. I will talk a little bit about how it could be done. But the complexity will be, like the span will be worse. Okay, what we're doing right now, we will do only one iteration of this bit algorithm. Only one. So to get from n to 2 logarithm n.
Mm-hmm.
Then we have the following. We have the pairs of x and color x. But each color x is less than 2 logarithm.
Yeah.
Okay. And then the next step I put onto the homework. I claim that I can sort these elements in of n work, O of poly log n span.
Sort means.
Sort by
by
color.
color.
By color. Yeah.
Uh-huh. Okay.
So let's simplify the problem. You have n elements, each of one not bigger than logarithmic n,
Mm-hmm.
and you have to sort them.
And ok.
Yeah, in this complexity. Then everything is fine in terms that we will have logarithm n colors, and we say C here is like logarithm n to logarithm n. Okay, and then we go level by level, applying the procedure that we had previously. And then in total we will have work is obviously linear, because what we did one level of this,
Mm-hmm.
one round of this, then the sort that works in linear time, and the total work here is the total number of elements in this arrays, which is linear.
Yeah.
So the work now is linear. Unfortunately, the span is a little bit tricky, and I will say it is poly log of n. I don't want to calculate this
Так.
precisely.
Okay, wait a second. What? We have sorted pairs color XX.
Yeah.
And how we get the result from it? I mean,
How you get from this?
yeah. Okay.
Put one.
Yeah, I mean it's
No,
they will be in the same array.
Mm-hmm. Okay.
You and of course you know their start positions
Mhm.
because you
Mm-hmm.
can calculate the difference between two elements, and this will be the borders of the arrays. And then we just go parallel for on this, on this, on this, on this, and on this. So
Okay,
it is logarithmic squared from here. The most questions is this polylog.
Mm-hmm.
How much it is there, but like I guess it shouldn't be worse than logarithmic cubic. Okay, that's the algorithm for symmetry breaking. What I could say that in the prom model you can have an algorithm in logarithmic time, and it is explained in 5 pages or something like that. So I'm not going because I mean it doesn't really have anything with the real life system,
Okay.
right? So like even here we are tricking a little bit because we say that the bit operations there are constant,
Mm-hmm.
which is not exactly correct if n is large. So
Mm-hmm.
it should be logarithmic n in the worst case. So it should, really, if you will calculate this work time, it will be n logarithmic n, unfortunately. But luckily, on the machines, we think that their arithmetics is constant.
Okay, where exactly we have applied symmetry breaking technique? In which place?
The symmetry breaking is the way to color elements so that they're not. This is the symmetry breaking.
It's just.
Why it is named so? Because you have like some random identifiers and next identifiers, and you wanna kind of to find what it is doing. It tries to find an independent set. So our goal is to have this independent set, so it will be bigger than n over 3.
Mm-hmm. Okay.
Of course, since you color this in 3 colors, then you will have independent set of at least n divided by 3. Like you can choose some color. This will be important in our next problem. We shall name it as list ranking. I guess you have no idea why we have symmetry breaking, right? Why we need this. Unfortunately, right now this will be the same. I will explain how to do list ranking with symmetry breaking, but not saying why we need list ranking. So like that will be on the later lecture. I don't know the time exact. Okay. Oh, we have 2 concurrent viewers. Wow.
It was 3 moments ago.
3 moments. Okay. So we have the list, and we have a guy like this. This is guy V, and we have next V.
Mm-hmm.
Then what we are trying to do? Like you are given this strange list with the next pointers, and you have nothing else.
Mm-hmm.
And you want to enumerate these elements by the distance to their end, for example. Or if you want to calculate the prefix sums. So like after the separation, we will have this guy will have a1 plus a2 plus an minus 1. This guy will have a2 plus a3 plus an minus 1, and so on. So like kind of suffix, we want to calculate suffix sums,
Mm-hmm.
but like that's for the beginning. We will calculate like just when ai are 1. So we just calculate the distance to the end there. How is it done? It is done pretty simply. Okay, but at first I would like to ask you whether you can come up with an algorithm that works in of n logarithm and work and of polylog span. Like in this complexity, could you come up with the algorithm?
Do we have only the pointer to the start. I mean,
We only have the pointer to the next. That's it. That's all that we have.
yeah, we have pointers for the next for each node, but and we have a pointer to the start. Yeah, of course, yeah.
No, we have only pointer to this guy.
To the end.
Yeah. And that's it. That's all that we know.
Then we can't reach others.
Yeah.
I mean,
Probably to
this guy is here. It points to itself.
Ah. Oh. Okay, got it. Well, firstly,
We did this. I'm pretty sure that in algorithms and data structures course, we were explained how to do that.
firstly we want to build links to the previous elements. Seems no, yeah.
No, we don't have. We can get it. The links to the previous element we can get the same way as we do for cycle.
Mm-hmm.
So we can get previous if you need it.
Mm-hmm. Okay. Then let's say, okay, we have links for each element to its left neighbor.
All right. I mean, it doesn't matter.
We can calculate the total number of nodes.
We know the total number of nodes. Yeah, we know. Like
Great.
Again. Oh, sorry. They're identified again as 1 to n.
Uh-huh.
They have identifiers here.
Okay. Okay.
Yeah, sorry. Like yeah, we have.
It means that. Firstly, let's find the middle element in this chain.
How would you do that?
Just by jumping from the end to the previous elements for
n over 2 times.
It.
Okay.
No,
That.
It means we have more than polylog span if we do it already.
No, I think potentially what you are discussing, yes, you can do. Yeah, I think you can do in n logarithmic time. Yeah, I think your approach should work. Like I mean, if we like we have n's of an array, so we just get to the guy, pass n over 2 elements here, like split it into 2 links, like say that this guy is the head of new, and then going recursively on both parts.
Yeah, but in such approach we have
we have span. Okay,
bad span.
We have bad span, yeah, because the span is linear here. Yeah. Yeah. Of course, but like the work is in logarithmic n. Yeah.
Yeah.
Why did we went from the end of the list, not from the beginning?
I mean, to find the middle element, it will still work like in linear time in any direction, right?
Okay, let's try something as the following. Firstly, we have link from each node to the right to the next, yeah, to the nearest right neighbor. Using parallel for, we can build links over links over neighbor. I mean,
Like in binary jumps, like
yeah. So,
to the neighbor in distance of 2, neighbor of distance of 4.
yeah,
and
build
so-
something like
Yeah,
binary jumps.
This is exactly what you want. What you need to do here.
Ah.
Yeah, this is binary jumping technique. So that you just for each guy you jump over 2 and like you recalculate the links. Like so you have next. Now you have next prime with answer there. And then after like you do this linearly per each iteration and in logarithm n times you will reach the end of the list, of course.
Yeah.
Okay. That's a pretty good approach. Again, we have like n logarithm can work, and what span do we have? I think it's quite reasonable. Should be something like
n plus log.
logarithm squared, I guess.
I have
Right.
one question.
Yeah.
Do we have random access to?
Yeah.
Ah,
You have random access. I mean, there is somewhere in memory you have like just next pointer. What?
No.
I just want to ensure that we don't have to run all over the list to get to like previous to the last or to the
No,
previous
you
to the
don't
last.
have to, because each time you like shrink their length from this guy to that.
I mean, if we have before, we still, I suppose, can just go to the end, because in the list we
can go to
in usual list we don't have like random access, and we have to go through all the array from the beginning.
I'm not sure
Wait,
that I
through
understand.
Sasha,
Constraints.
Sasha says that in lists, in our understanding, we have we don't know the full set of pointers of on each element. So we have only one pointer to one element, which.
Okay, yeah, sure. You have the pointer like ID, which points to this node.
Mm-hmm. Okay.
For each node.
Yeah.
No
I mean, we can do that if we want.
Yeah, we can do that, but in linear span.
Linear span.
Yeah.
Why?
We still need to traverse the whole list to save these pointers.
No, I just say that I will create the list of nodes. So what I'm given, I have next, right? I have
Yeah.
array next with their identifier here and like some identifier prime here. Like next of ID is ID. Then I just create and like nodes as they are. The class of nodes that will link me to the next.
So this is the list where nodes are in array.
Yeah, we are working not on pointers, but just on array which has random access. Yeah?
So we have an array of nodes where their traverse order is not like from left to right,
Yeah.
but in some. Okay, so and
Still don't understand what you were. What was the
We
question?
concluded that all our nodes stored just in one array, and links just
points.
just points in some random order, not from left to right. In
No,
this
they're
way, yeah?
they're not necessarily from left to right. There can be like that.
Yeah.
No,
Yeah. Okay.
It can be.
yeah, we got it.
Yeah.
Okay. You meant like that they're 1, 2, 3, 4, and so on?
Mm-hmm.
No, like they're in random. Like they have random shuffle. Okay. Okay, the question number 2.
Mhm.
We know how to do symmetry breaking. What we can do with that? We have, from the symmetry breaking, we know how to get an independent set of size at least n/3.
Mhm.
So we can find independent set in of n bigger than equal than n/3 in of and work and of polylog. I'm sorry. So if we get independent set, so for example, sorry. So that this guy and this guy are in our independent set. So what we can do with that? Can we throw these elements away?
Mm,
We can.
no,
Okay, another.
because we are counting prefix sums.
Okay, another question. We can write on each node, as previously, the length to the next, like the length to the next. So in our binary jumping,
Mm-hmm.
we had in binary jumping we have like we replace like that next
Yeah.
and we store the length, so it becomes 2,
yeah.
right?
Mm-hmm.
This will be next x. This will be the new next, but with another length.
Mm-hmm.
Okay.
Oh.
So can we do something with this independent set?
No.
May we somehow know the lengths between these two nodes that are in one set?
Yeah, I mean you are almost close. Let me then explain, possibly because it's pretty hard. I will just say that for each guy, which is an independent set, let's say I will kill him and throw him away. I like if here were like P and Q, I would say that this is P plus Q, and then throw away these guys. To be more precise, I will filter them out for the future when I will revert everything back.
Mm-hmm.
So like, because our independent set is at least n/3, then like the new size of the list is 2
Yeah, sure.
2/3n.
Mm-hmm.
And then again it's like 2/3 squared n and so on. Then the only problem is how to restore everything. You specifically save for each closed guy its previous and next,
Mm-hmm.
and then when you put it back, you just know this path. You just know this path, and since this guy was knowing the length to the end, then the length of this guy is like Q plus this ans for x.
So probably we can just after each symmetry breaking store the result in another array.
Yeah,
or
for
something
example.
like that.
For example, like their idea is that the ones that are like the ones from the independent set, we can remove them, like store it somewhere, and then on the way back we can put it back to recalculate their distances. Okay. What will be the complexity of this thing? Is it clear that the work is linear?
Linear. Work. Yes, because we have each node deleted only one time. And
I was trying to calculate this. Like at the first round you have n elements, on the second round you have 2/3 n elements,
yeah.
and so on.
Then
I mean in total, yes. So like to find the answer in total, so you have to apply this till there.
No, it seems you are trying to calculate span, not work.
No, I'm trying to calculate work. I mean, in the first level, you run symmetry breaking on n elements.
Yeah.
You throw away n/3,
Yeah.
and you're left with 2/3 n elements.
Yeah.
Then you run symmetry breaking on that,
Mm-hmm.
throw away bad elements, have this one,
Mm-hmm.
and so on. So your total work will be n plus 2. 2/3 of n plus this, and so on.
No, we can just use master theorem.
Yeah, it's linear, I think. And while the span is still unknown mystery, but it is polylogarithmic of n. I think this is pretty sure, because each symmetry breaking is polylog,
Mm-hmm.
and we have logarithm n levels.
Mm-hmm.
Like logarithm n times you have to shrink it, so it will be okay. Then an interesting question arises. A very interesting question arises. Can we make the span faster using this? Because here,
Maybe on
here, I will give you a hint. So here we have some polylog of n, which is, I guess, it should be something like log 4 of n, or log cubic.
yeah, maybe from one step we can use our previous solution, which is
Yeah.
binary.
Yeah, that's accelerating cascades here. So you can get simply the improvement here. So you stop at n divided log n here, and then you apply this algorithm. Then in total we will save, like it will be not log cubic n, but it will be log cubic and log n as per usual.
Yes.
Like we have to make log n of these steps to
yeah.
get to n divided by logarithm n, and then we call this algorithm and then I think in this case the algorithm will be working faster. I mean this guy has no complexity on, like no constant here. Binary jumping technique it has almost no constant there, while their symmetry breaking is like it's like comically worse. So that's an example of an algorithm where like accelerating cascades make sense. Okay. Luckily, in prom model there is an algorithm that works in logarithmic span, in logarithmic time.
And
Like-
it is 10 pages, yeah?
Yeah, something like that. No, it's not 10, it's less, but still it counts some potential, some crazy potential, and I'm pretty sure that, again, on real world machine, that prom algorithm will work with additional logarithm, because they don't care about parallel force. Like I don't think it's pretty good here. Now let's go, like it depends on how much time do I have really.
About 10 minutes.
About 10 minutes. I will say that. Randomize this trunking, which is much simpler than everything that you've experienced before. It is again, why it is named randomized is that our search for independent set will be randomized. So what's happening here? So we have this list. And then you do the following. Each guy in parallel flip a coin.
Mm.
And it has like heads, tail, heads, oh, little bit tail, and so on. I would say the following. I will take all the guys for which it is tail and its next is head.
Mm-hmm.
Only next?
No, we check that it is a tail and the next is head.
No, I mean, we don't check previous.
No, we don't check. I will show it right now. So, and I say that this guy will be kicked out. There is a tricky problem is that there are no normal random generators for parallel systems. That's worsens the thing. But I mean, you can, like, there are two options, right? Either you use local random generator for each processor, then everything is kind of fine, or you use pseudo-random function that will give you a random one in constant time. So, for example, you put ID there, and it returns you some random number. Okay. The question is the following. So again, I'm pretty sure that you understand why two neighbors can be extracted at the same time, because like this guy should be tail, and if this is also tail, then his neighbor is not H, right? So like so we don't care about previous, but we care about these guys. Okay. What is the expected number of elements that are thrown away?
And divided by 4.
Yeah. Why so? Because like at first their expected number is linear in the terms of, so I can independently consider each element, and each element satisfies us with probability 1/4.
Yeah.
So the total expectation of x is n/4. Unfortunately, their expectation doesn't give us anything about complexity of the algorithm, because sometimes it can be n/4, sometimes it can be something strange. So we need a little bit more tighter proof. So I will say that I can do this in, again, there will be logarithm steps with high probability. I will say.
This high probability.
What is with high probability? The high probability means that I would say that that there is some alpha which is bigger than 1.
Okay.
and I say that the algorithm will work with logarithm n times with this probability. What we're doing, at first we get their independent slots, so we split them into their pairs of 2. So that, like, for example, right now this guy cannot be thrown away because it depends on this, and they're in the different blocks. So like we a little bit worsens our situation because in expectation this will be n over 8, right? And the number of them is n over 2, the number of blocks. Okay, I will state their Chernoff bound. I need my laptop for that. I need my laptop for that. Okay, Chernoff upper tail. I don't know whether you was explaining that. I'm not 100% sure. Like if delta is from 0 to 1, then probability of x bigger than or equal than 1 plus delta of mu less than equal than e in the power minus mu delta squared divided by 3. So this I need. So what does it mean? We have n random variables. We have n random variables here, and this guy is x1 plus x2, like plus xn, this random variables, and then mu is expected of this x1 plus x2 plus xn. What we're going to do, I will just, so we have n over 2 random variables for each of these guys. N over 2 variables here. And I want to prove that the number of failures, vice versa, number of failures is relatively small.
Failure is when we don't kick out.
Yeah, if we don't kick out the guy here. Yeah. So I will be trying to prove that I will shrink at least n over 16 elements. I will try to prove that with a very high probability, n over 16 elements will be taken out.
I have a question.
Yeah.
If we have already broken them into pairs of 2, why don't we just kick out the first element in each pair?
We don't have this. This is for the proof. I'm just consider I just consider them in pairs, so we will have independent variables, and I will prove exactly for this independent variables. Okay. Let's say the probability of the failures. So like failure 1 plus failure 2 plus etc. plus failure n bigger than equal than 1 plus delta multiplied by how much? Like we have n over 2. Then we throw this guy and this guy. This is with probability 3 over 4. We got bad. Like we have Fy is with with probability 3/4. You have n/2 variables, and fy is 1 with the probability 3/4. Thus, we will get 3n/8. And since I want to have n divided by 16 elements to be good, then I need that 1 plus delta 3n/8 is equal to n/2 minus n/16, because we have n/2. We have n/2 blocks, and I want that n/16 will succeed it, at least. I will continue, so this is 7n divided by 16. So,
Okay, yeah.
if I will prove that f1, f2 plus fn/2 bigger than equal than 7, and this is small, this probability, then if I invert it, I will get n/16 for their positive probability. Okay, so I need to calculate the delta now. It's not so easy. Should be somewhere, somehow. 7/6. Delta is 1/6. Because like this will be 7n divided by 6. Then you throw 3's away and you get 7n divided by 16.
And
I mean, it's clean math. Like you don't have. You can believe in that right now. This guy is a minus 3 n divided by 8 with 1/6 squared divided by 3, and I don't care, it will be in the power minus c. With n, of course. If it was not for n, then. Then, right now I will cheat a little bit. My proof will be a little bit simpler than usual, because typically, what typical people trying to prove, they say, I will say that the probability that I will make bigger than equal log n good attempts with bigger than equal than logarithm n tries. I mean, we have, as you can see, right? We start with n, then we throw, like, we have next iteration, have next, and so on. And they prove that out of the, like, we say that the iteration is good if it shrinks by some constant. Then to get to the constant size, we should make, like, logarithm n good steps. And if, like, typically the proven is if the number of steps is c logarithm n, then the number of good steps is at least logarithm n. So that is what typical is trying to prove, everybody. But I will cheat here a little bit. I will say that I can get this array to the size of logarithm n. Just to the size of logarithm n. So, and after that, on the list of logarithm n size, I will just do everything sequentially, and it will fit in our bounds. algorithm
Okay.
for our span bound, so like I don't care. Okay, so I will calculate the probability that everything is successful, that all the steps are successful in our algorithm. So it is 1 minus e in the power cn times, so the probability is less than or equal okay, I think I want like that. I will prove that the probability is good. I want to I say that the probability of that like I want to calculate with what probability I will always be successful. Okay, so this means the first one is successful with the probability of 1 minus this thing. Okay, then it shrinks in like another constant dn, and 1 minus e minus c d squared n, and so on and so forth until we add with minus c d logarithm n in there, I guess at worst in logarithm n. Okay. Do I have logarithm n? Yeah, I think I will decrease. Okay. So how many steps there? There are logarithm n elements, right?
Logarithm n.
Like there are logarithm n brackets here.
Yeah.
Because we divide by d and we want to get from n to some reasonable. I will lower bound this by this thing. I will lower bound by this, so it is bigger than or equal than 1 divided by 1 minus minus cd log n in the power of
log n.
Power of log n. This is bigger than 1 divided by logarithm n by Bernoulli minus cd logarithm n. cd in the power of logarithm n logarithm n. Something is not right. Something is not right. I thought that this guy should be very small. Ah, yeah, of course, because there is no. Yeah, that explains a lot. Yeah, there is no this guy. Sorry. When because it was already d in the power logarithm n.
Okay.
Yeah, so like that's why I was confused here. Yeah, so it is c times logarithm n, and this d will just calculate us that the total number of these brackets is logarithm n. Okay, so we have this, then we have this, and as you can see, this will be equal to 1 minus logarithm n times 1 divided by n minus with the power c. I will just
No, yeah.
e in the power logarithm n, and as you can see, this is almost like we can choose constant here, so it will be fine. So that is how we get with very high probability, we will be always lucky. So each round of shrinks very successful.
Mm-hmm.
So we proved that the algorithm works in logarithmic n time with high probability.
Mm-hmm. Okay.
That's it. So we proved that the randomized list ranking is also working well with high probability, so like it doesn't, and it is much easier to write
Much easier to write. Ah,
because you
no.
don't need to make symmetry break. Like it's this randomization kind of says that this is very good for symmetry breaking the random variables. So okay, let me then state the homework for the next lecture. So that we had two problems already. We need to sort n elements which are not more than logarithm.
Mm-hmm.
It's one task. Another task is how to perform deletion of the elements from 2, 3, 3. And the third one is quite interesting. Is that you are given a tree
Which tree?
what? Okay, suppose we're given binary tree.
Okay.
Yeah, binary tree. And what we want to do, we want to color all the elements in how much time I want. I think in all fan work. Let me be. I will state log star n work of polylog n span. You have to color the tree in 3 colors such that none of the 2 vertices are connected with the same color. So it is instead of list, we wanted to do this on cycle. We did it on cycle, and right now we do this in the tree.
3 colors?
Yeah, 3. This is PID. We know the parent identifier. I think you can do this in linear time, to be honest. But I'm not sure. I'm not sure you can do that.
Yeah, probably it's 3.
Well, it can be done. Okay, if you will do this in offline work, then I will give you extra points. Plus 0.5.
And also polylog span.
Yeah.
Mm-hmm.
Because I can't right now understand, can I do this in linear time? I guess I can. I know how to do this in logarithms and logarithm star time. But I guess I can do this. I mean, this is kind of should be the same as with the recycle. I mean, this kind of consequence should be the same as for the cycle, I guess. Okay, that's it for today. Thanks for coming.